Yes.
Okay, perfect. Well, welcome to the webinar 2025. The subject is the advantage of solution-based analyzers based on ion exchange chromatography with pulsed aperimetric detection. My name is Martin. I'm 23 years at Antec, and I'm happy to be able to start this short introduction. Antec has the headquarters in Alphen aan den Rijn since 3 years, which is about 20 kilometers south of Amsterdam. We have a subsidiary since 2010 in the United States, direct sales and service, as well as in the DACH area, the German-speaking part of Europe. Over the years, we have received a lot of questions. What is the difference between HPLC and electrochemical detection and HPLC with regular UV fluorescence or whatever? Well, actually, there's not a big difference. And I'm going to show you quickly why not it's different from each other. Actually, you have a regular HPLC system and you have your separation. And finally, after separation, the compounds will elute and you will detect. With electrochemical detection, instead of light-based detectors, you will oxidize your molecule, mainly, sometimes reduction, but oxidation means a donation of an electron, and the electron is the current, and that's what you measure. A couple of rules will be covered today, so I will not go into details. If you speak about carbohydrate detection, you have oxidation on your gold electrode. And as soon as you do that, which we'll also explain very well in detail later on, you will contamination on the electrode, and that finally will result into a loss of signal. To keep this signal constant, you have to clean, and we do that with a pulsed aperimetric detection mode. Antec started in 1990 as a spin-off company from the University of Leiden, and the first detector was shown here on the left side, which was at that time the most sensitive detector in the world because they were looking for dopamine and serotonin levels on picomole levels. So that was very low, and it was by far the best one. Over the years, we got more and more requests. Can you supply us a system? Because when we were installing the detector, it was taking an hour, 2 hours, sometimes 3 hours, but we spent a couple of days on tweaking and optimizing the LC system. So finally, based on requests from customers, we have also seen a lack of experience in electrochemistry. We have launched our first ALEXYS Analyzer. And over the years, we have a couple of versions. And in 2023, we have introduced our latest version, which is shown here on the right side of the slide. Also in that year, we finally were able to launch our SweetSap column, ion exchange column, and the result of that was that we were able to supply a complete solution, a carbohydrate analyzer, the hardware, the chemistry, and the applications. The applications are dedicated and guaranteed, and you can find a lot of them on the website. So we did all kinds of experiments for beer industries, the coffee, etc., etc. All this is packed into an analyzer. Improved analyzer give you a stable performance with superior chemistry. All the details, how we get there, will be explained in the next part of the PowerPoint presentation of this webinar. I hope you like it, and thank you for your first attention.
Thank you very much, Martin, for your introduction and insight into Antec Scientific. Please let me have a quick look in the Q&A pane if there are already questions. No, I haven't seen any, so thank you again, Martin. We'll now move on to the main part of today's webinar. Our first speaker is Detlef. Detlef, what do you have for us today?
Well, what do I have for us today? First of all, we have the expert audience. Second, we have a slide deck. And third, we have the time. So let's talk about high-performance anion exchange with pulsed aperimetric detection. We will discuss the separation of carbohydrates using anion exchange chromatography and pulsed aperimetric detection. We will cover hardware and specific solutions and define an analyzer. Before we proceed, however, let's first discuss the prerequisites. How can we separate carbohydrates? How can we detect carbohydrates before exploring the entire instrument concept? Okay, let's do that. When we discuss sugars and carbohydrates, components such as sucrose, glucose, fructose, and galactose may come to mind. However, these are neutral sugars. We need an ionic component to analyze and separate them using anion exchange chromatography. Now, how can we utilize anion exchange chromatography to separate neutral sugars? Let's examine some structural properties that carbohydrates share. Now, what do we see on this slide? It's straightforward. Some of the components I mentioned earlier are glucose, fructose, mannose, cyclose, or allulose. These are sugars, monosaccharides, neutral monosaccharides. What do they all have in common? They are alcohols, polyalcohols or polyols. And what we know is that an alcohol is a weak acid. So if we want to generate some anions, if we want to generate some anions from an alcohol, we need to deprotonate it. But the question, ladies and gentlemen, is at what pH do we do that? In order to answer this question, let's have a look to the next slide. We have defined sugars as polyalcohols, polyols, and they are weak acids. So it becomes clear that the acidity determines the pH required for the deprotonation. Specifically, the negative logarithmic value of the acidity constant, that's the pKa value, indicates the pH at which 50% of the carbohydrate, or generally speaking, of the analyte, is dissociated. If you examine the table on the slide, you will see the sugars listed along with their pKa values, and focusing on the pKa value, you observe that they range from 12 to 14. Ladies and gentlemen, this is why high pH values must be applied to deprotonate carbohydrates and generate oxyanions. This is why a carbohydrate analyzer needs entirely metal-free flow paths. At those pH values, metallic alloys like stainless steel or titanium alloys corrode and release metal cations, which are the enemy of a good carbohydrate separation. Christian, will you take us through the basics of the anion exchange process?
I would be very happy to do so. Well, thank you, Detlef, first of all, for a wonderful explanation about how to deprotonate the carbohydrates. And now let's talk about how to actually separate them. So let's assume that you inject your sample into a high pH environment where it becomes deprotonated, and that will form carbohydrate oxyanion. This carbohydrate oxyanion, they will be retained on the positively charged anion exchange resin in the column. That's what you see here on the right-hand side of the slide. Well, next, the eluent, they comes in, right? It can be hydroxide, it can be acetate ions. These ions in the eluent, they are also anions, so they will compete with the carbohydrate oxyanions for a spot on the positively charged stationary phase. So the carbohydrate will be finally eluted or separated by these ions, and it could be earlier, it could be later, depending on how strong the carbohydrates are retained. So the carbohydrates will be separated as oxyanions. They will follow mainly the rules of anion exchange chromatography. And what are those rules? Well, there are 3 parameters that controls carbohydrate retention. The first one is the degree of polymerization, or in short, dP. In a classical ion chromatography, you would call it size. So the smaller the carbohydrate, the earlier it elutes, and the larger the carbohydrates, the later it elutes. It's very simple. So size really matters. As a second parameter, we have charge. The rule is as easy as 1, 2, 3. So if you have an analyte with a single negative charge, it will elute faster compared to double or triple negatively charged one. Or if you have amino sugars with a lower negative charge density, they will be retained weaker on the stationary phase relative to the corresponding neutral sugars. So we have size, we have charge, and the third one is polarizability. So this is about absorption and desorption of an analyte on the anion exchange resin. For example, if you have a sugar with modified functional groups, this allows the sugar to be more polarizable, and therefore it can stick better on the stationary phase, making it elute later compared to the non-functionalized sugar. So in a nutshell, these three parameters are responsible for the carbohydrate retention in high-performance anion exchange chromatography. Remember size, charge, and polarizability. Well, to illustrate better, I brought this chromatogram to the slide in front of you. You can see that sugar alcohols, the alditols, they elute at the beginning of the chromatogram. Why? Because they are the weaker acid compared to the other sugars here. Next, we have monodisaccharides followed by oligosaccharides, eluting in the order of their acidity and size. And lastly, we have uronic acids here, which carry a charge because they are easier to deprotonate and therefore making them more negatively charged and retained longer on the column. Additionally, let's pay attention to the chromatogram peaks because they are really sharp, right? They are really nice. What about the resolution? Have you ever seen the separation between arabinose and rhamnose or xylose and mannose like this? Well, let me tell you some secrets to achieve this exceptional separation. It is because we use SweetSap AX20 column here, which has a superior performance compared to the other columns available in the market. Well, let me tell you one more example, and this example will be about size. Let's have a look at this separation. This is a gradient separation of inulin. This is using sodium nitrate instead of sodium acetate as the pushing ion. And sodium nitrate is a stronger pushing ion. And that's the reason why we can elute polysaccharides up to DP90. DP90, that means 90 monosaccharides chained together. And that's a huge molecule. Isn't that amazing? Well, let me tell you another tricks to achieve this separation. It's not a secret anymore that we use our own SweetSap column. In this case, the AEX200. And here we utilize the temperature. First of all, the separation temperature is 35 degrees Celsius. This is to sharpen up the peak shapes. And the detector temperature at 45 degrees Celsius to enable higher sensitivity to detect this high DP molecule. Additionally, we also set the autosampler temperature at 40 degrees Celsius. And you might be wondering, wait a second, I usually put my food in the fridge or freezer to preserve it. And now you're telling me to put the carbohydrates not in the fridge, but at higher temperature? Well, in this case, yes, we must consider the solubility of these oligo and polysaccharides, because the larger the oligo or polysaccharides, the lower the solubility. And that's why we heat the autosampler to keep them dissolved. And now let's take a look at the separation, how sharp the peaks are, how well they are separated, and look at the retention time. It takes half an hour, 30 minutes, for a gradient run to separate basically 90 components. Yes, there is some re-equilibration step here, as you can see in the slide, but this is mind-blowing how fast the separation can be. Well, I have explained a little bit about detection, so I believe that you might want to know about detection and that's why I will bring it back to my colleague, Detlef.
Thank you, Christian. Let's continue with detection. And first of all, let me comment on the separation. It is really mind-blowing. 30 minutes, when I saw it the first time, I couldn't believe it. It is wonderful, wonderful separation. Now, switch back, let's talk about detection. Let's talk about detecting carbohydrates with the highest possible sensitivity. In this schematic, you see the gradient pump on the left, where the eluents are being mixed. The eluent takes the sample from the injection loop to the column set into the amperometric detector. We first recognize the eluent flowing through the cell, but nothing happens. Why? Because the eluent is being selected so that no reactions with the working electrode will happen. Sodium hydroxide and sodium acetate are electrochemically inactive under the given conditions. That changes when you take your sample and inject your sample. Well, what happens if you inject a sample? Let's pretend we inject a sample with two components to detect. Please keep an eye on what happens when the components elute, okay? Now let's start the chromatogram. First we see a baseline, then a negative water dip, then the first analyte elutes, and some carbohydrates diffuse to the gold working electrode where they get oxidized. Now the second component elutes, a peak is generated, and once again only a fraction of all components is oxidized. The oxidization current is what we measure as a concentration proportional value. This phenomenon is characteristic for amperometric detection. Between 3 and 5% of the injected analyte undergo oxidization. Electrons are released, generating the oxidation current. The oxidation current is directly proportional to the concentration because mass transfer to the electrode is diffusion controlled. It is not electrolysis. Now let's talk about the sensitivity of the amperometric detection. To discuss, I brought this reaction with me consisting of 3 steps. This reaction scheme is inspired by a publication of Johnson and Lacourse, and you are going to hear more from these 2 gentlemen. The reference is given on the slide. You see the 3-step oxidization of glucose at a rotating gold electrode. What makes this reaction so interesting is that 1 molar of glucose generates 10 molar of electrons if you count them. 2 electrons, 8 electrons, 10 electrons. That's, if you so want, an amplification factor of 10. That explains why amperometry for carbohydrates is so sensitive. There's something else. If you look at the reaction, you notice that it is pH dependent. See the protons here, 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 and here. And what we learned through our education is that reducing or increasing the reactant's concentration can influence a reaction's equilibrium. Now, in order to push the equilibrium to the right, you should remove the protons, right? But how do you remove protons? By adding or ensuring the presence of hydroxide, an acid-base reaction. Therefore, ladies and gentlemen, the sensitive detection of carbohydrates favor high pH environments in the detector cell. The rule of the thumb that we developed at Antec with our detectors and detection cells is that hydroxide eluent concentrations below 10 millimoles per liter favor higher carbohydrate concentrations and an extended working range at higher concentrations. Lower concentration work, trace analytical work, is favored at eluent concentrations above 10 millimole per liter due to the increased detection sensitivity. But what do you do if, say for chromatographic reasons, you need to use very low hydroxide concentrations, say below 1 millimole, or even water as the eluent, described in the literature? The pH in the detector cell will be too low for a meaningful detection of the carbohydrates. In this case, you add some sodium hydroxide after the column in front of the cell. This is called post-column addition of sodium hydroxide. Now, let's have a look to this slide. This slide discusses the amperometric detection on a gold electrode. And I would like to begin with a question. And you will likely say, well, what does that has to do with carbohydrate detection? Well, wait a second. Have you ever made caramel? One of the first steps of making caramel is melting sugar in a skillet, and which requires some skills to avoid burning the sugar. Now, that's exactly what happened to me once. So sugar burned and I had to clean the skillet. And let's cross the fingers that you decided to use a stainless steel skillet, because you could easily scrub. Now, how does this story relate to carbohydrate oxidation at a gold electrode? Well, both involve reactions of carbohydrates on a metal surface and some cleaning. However, you don't scrub a gold electrode like a skillet. And again, Johnson and Lacourse proposed using one potential for carbohydrate detection and additional potentials to remove the oxidation products. After cleaning, the electrode must be pure gold. So the common pulse sequence shown on this slide consists of 4 potentials. Now, what do we have here? We have one potential here, second potential here, third potential here, fourth potential here, and this all is happening in a time scale of less or equal half a second. So that is the so-called 4 potential pulse sequence. It enables measuring, cleaning, and reconditioning with a data acquisition rate of 2 Hz, 2 data points per second. And that is the fastest in routine pulse amperometric detection that we know. Now, this slide mentions this 4 potential waveform as the preferred waveform for carbohydrates, indicating others exist, like triple pulse waveforms for specific sensitivity or matrix needs. And there is even one more allowing for a data acquisition rate of 3 Hz. The 4 potential waveforms are preferred for their high stability, minimal wear on the gold electrode, fast data acquisition rate, and high sensitivity. Today, approximately 90% of HPAC pad applications for carbohydrates use this sequence. Now we know how we deprotonate, now we know how we separate, now we know how we detect. Now, I think it's time to discuss the hardware. Christian, will you take over?
Yes. So as we all can see here, we will talk about the hardware. What you see on the screen is our solution for the perfect HPAC pod analysis, and Martin has actually introduced it a little bit in the first part of this meeting. So we call this instrument the ALEXYS Carbohydrate Analyzer. And let's go quickly through all the modules in our ALEXYS Carbohydrate Analyzer. We will cover the ILUAN tray, the pump, the autosampler, a column thermostat, and last but not least, the Decade Elite electrochemical detector. Please don't expect us to dive very deep into specifications. And if we need to discuss specifications, we can do it after this webinar. So now let's start to talk about each individual modules. And I will start with the ILUAN tray. The ILUAN tray that we have is called ET210. And as you know, degassing the ILUANs is one of the most important steps to achieve a perfect liquid chromatographic analysis. In HPAC pod analysis, it's even more important because the mobile phase contains an alkaline solutions. So it can react with carbon dioxide from the surrounding atmosphere, creating carbonate ions, which are also anions. So your retention time will not be stable if you have carbonate in your mobile phase. And that's why we need to degas the ILUAN. And for that purpose, we are using our ET210. Well, this module can be used not only for degassing by the means of sparging, but also by pressurizing the headspace, and that means to keep the eluents under an inert gas atmosphere. When I first started at Antec, it's amazing. I have never seen such a device before, and it's amazing because it can allow 4 polypropylene bottles to be simultaneously degassed. Secondly, it's also connected to nitrogen source, which is more cost effective compared to the other inert gas available. Additionally, it's very easy and safe to use. How? Well, it features a quick connect fitting. Well, the quick connect fittings are equipped in the gas line and also the liquid lines. And it has a feature called self-sealing. That means you do not have to worry about splash or eluent leak when you connect or disconnect the tubings, even though your bottles are pressurized. Well, that makes it very safe, and that makes the ET210 a perfect solution because it combines low cost and very efficient removal of carbon dioxide, and that ensures retention time stability. Next, we have a pump and column thermostat. The pump that we have is called the P61L. It starts with an integrated degasser, so it's built in the pump. And the pump itself is a metal-free pump with the quaternary low pressure gradient. I would tell you that this pump is one of the key modules in the ALEXYS Analyzer because that ensures the best possible baseline performance thanks to its active electronic pulse compensation. So this allows us to have a very minimal pulsations and therefore a stable baseline. Next, we have a column thermostat. And as you know, temperature is very important to ensure retention time stability and ultimately the analyte identification. So this column thermostat can be operated from 5 to 85 degrees Celsius, and it's very stable once it reaches the desired temperature. In liquid chromatography itself, we often use elevated temperature, but I also encourage you to try to work at lower temperature with carbohydrates, because you would be surprised at how much resolution you can gain from lower temperature. Next, we have the autosampler. It's a metal-free autosampler. And what exactly does an autosampler do? Well, it's not a surprise anymore that it will inject your sample. And I want to emphasize one particular feature of this autosampler, that it allows you to inject a very viscous sample at a consistent flow rate without air bubbles. That is thanks to its pressure-assisted sample aspiration feature. The autosampler is also capable of heating and cooling. Well, as I mentioned earlier in the inulin separation, we heat the autosampler to improve the solubility of the sample. And here it is, the DayKit Elite electrochemical detector. This is the most versatile, flexible, and stable electrochemical detector. And it features its own heated detector compartment. So if you want to not having the column thermostat, it's also possible. You can combine it with the ECD itself. It can be 3, 4, 5 steps pulse mode. It's available with this detector, or even up to 30 steps in the new MPAT mode. This is suitable for applications as described in several literatures. So look no further, the sky is the limit. However, it's not just about flexible or versatile. Effective data handling and signal-to-noise ratio improvement are one of our strongest suit here. We developed advanced digital filter, ADF for short, and unlike other filters that depend on averaging, the ADF is a low bandpass filter. It allows low frequency signals, so for example peaks, to pass while filtering out the high frequency noise. And this results in a much more improved signal to noise ratio. Well, now that you know about the decade elite detector, of course, it doesn't work alone. You will need a flow cell, and the flow cell in the decade elite is easily exchanged. Now I hope you are curious about the flow cell, and for that I return the floor to Detlef.
Thank you, Christian. Yes, now let's have a look at the different cell designs. We basically have two cell designs available. On the left, here, you see the so-called flex cell. As you can see in the little schematics below, it is a thin layer design where the column effluent is sent across the working electrode at an angle. In this design, the available electrode surface and the cell volume are defined by the spacer, also called the gasket, placed between the working electrode holder and the counter electrode. The cell is used for triple pulse sequences, DC amperometry, and when you frequently change working electrodes or working electrode materials. To the right, you find the so-called sense cell, which has a wall jet design. Now, what is a wall jet design? A wall jet design means that you direct the sample stream onto the working electrode at a right angle. The entire surface of the gold electrode becomes accessible for detection, resulting in a larger oxidation current, which is where the name sensitivity originates. Hence, we recommend sense cell for carbohydrate determination due to its high sensitivity and outstanding performance with the four-pulse sequence as we discussed. But there is more. What if the sense cell allowed continuous working cell volume adjustment without any gasket? On this slide, you see the assembled sense cell here and a small handle here to adjust the working cell volume by turning it. So you can fine-tune the working cell volume and therefore adjust the sensitivity. In other words, the lower the working cell volume, the higher the sensitivity. The larger the working cell volume, the lower the sensitivity. With thin layer designs, you would need to exchange the spacers or the set gaskets. Here, use a small tool and adjust it. The graph on the right side of the slide shows the effect of adjusting the working cell volume. You see here, the higher the cell volume, the lower the oxidation current, and the lower the cell volume, the working cell volume, the higher the oxidation current. Now, everything has two sides, every metal has two sides, so there is a little catch though. You have to be mindful when adjusting this, the working cell volume. Why? The lower the cell volume, the higher the back pressure. Now, using the smallest cell volume with the highest flow rates might not be the best idea. In this scenario, we suggest using smaller inner diameter columns like the 2.1 millimeter sweet step columns we offer. This would positively impact the sensitivity as well. We just talked about columns. I think now it's the time to briefly examine our column technology. You know that columns in liquid chromatography are the heart of the chromatograph. Without columns, there's no separation. Instead, you would be performing flow injection analysis. Nothing's wrong with FIA, but I prefer the selectivity and the specificity of a separation over that. So let's discuss the sweet step column technology a bit more. We provide two versatile columns, the Antec Scientific sweet step AEX20 and the sweet step AEX200. The term AEX refers to anion exchange, and both columns are made from polymer materials. What makes them multi-purpose? At Antec, flexibility does not always involve switching between columns, but rather customizing elements, primarily the aqueous sodium hydroxide or the sodium hydroxide with sodium acetate elements being used in HPLC pad for carbohydrate analysis. The SweetSep AEX200 functions as a universal column, adaptable to various analytical tasks by adjusting elution conditions and chromatographic parameters. This includes isocratic and gradient elution, as well as examining mono, 2 oligo and polysaccharides. We employ a range of pushing ions such as acetate, you heard nitrate, and methane sulfonate. Our applications cover numerous market segments, as illustrated. The exchange sites feature quaternary amines, and the unique polymeric design of the columns ensures stability in pH and compatibility with solvents. The SweetSep AEX20 optimally analyzes monosaccharides, disaccharides, oligosaccharides, amino sugars in various matrices, including glycoprotein analysis, food applications. It offers excellent resolution for mono, di, oligosaccharides, and the use of quaternary amines and ternary amines give the AEX20 its unique selectivity. The chromatograms shown before illustrate this selectivity and separation capabilities. Why? Superior chromatographic selectivity and efficiency. How? I will show you shortly. We also have dedicated trap columns. The borate ion trap column removes borate primarily from the deionized water used in the lab, preventing carbohydrate peaks from tailing and improving chromatographic results. The amino acid trap removes amino acids from samples. So the borate ion trap is positioned between the pump and the injector, while the amino acid trap is between the injector and the column set. Now let's discuss the column architecture of the SweetSep columns. They all follow the same setup. We have a polymeric central particle, which you might want to refer to as the core. The central particle has a diameter of 5 micrometers and is monodisperse, meaning it has a very narrow size distribution. A very narrow size distribution translates chromatographically into small contributions to diffusion, resulting in sharp and efficient chromatographic peaks. This efficiency is further supported by the second aspect of the column design, the nanoparticle surface modification, which is quite simple. We sulfonate the central particle, and then we add a second polymeric particle, being totally aminated, that is significantly smaller than the central particle. Now, to give you some numbers, the diameter of the central particle is 5 micrometers and the diameter of the nanoparticles are approximately 0.15 micrometers. We combine the two emulsions of the positively charged nanoparticles and the negatively charged central particles. The nanoparticles agglomerate on the surface of the core particle, and we achieve a particle whose size and consequently the column back pressure is defined by the central particle or the core. Chromatography, however, is performed on the nanoparticles, which explains why we observed such high chromatographic efficiency alongside specific selectivities. You know the old rule in HPLC, the smaller the particle you use for separation, the more efficient the peaks become. Selectivities that lead to the separations you saw before. So separations that can be performed routinely daily, thanks to the improved design of the SweetSep columns. Now let's suppose your interest in chromatographic separations is as high as mine. In that case, you will be happy to hear that the next session of our webinar series, which is scheduled for June 26, is exclusively about applications. We talked about how we deprotonate, how we separate, how we detect. We talked about columns. Let's talk about quantitation a bit. Ladies and gentlemen, you have recognized that some calibration functions appear linear when running carbohydrate applications with amperometric, while others are more curved. And there are reasons for that. What I'm about to show you is based on what was published by Johnson and Lacourse, again. It discusses 3 different mechanisms by which carbohydrates can be oxidized on the surface of the gold electrode. Let's start with the first one. And the first one is the so-called transport control. What you see is the carbohydrate comes in, gets oxidized, moves out. So nothing happens in terms of passivation of the gold electrode. It is a fast in, fast out, and that results in a linear calibration curve. In contrast, there's the so-called surface control. Surface control means that the carbohydrate comes in, gets oxidized, and during the oxidization process, either at the beginning or at the end of the oxidization process, gets adsorbed on the gold electrode. Now, if it gets adsorbed, it takes away active gold surface for the oxidization of the new incoming carbohydrate, and that leads to a curved calibration curve, a strongly curved calibration curve. And then there's number 3. Number 3 is, well, life is not black, life is not white, so life is everything in between. That's why it's called mixed control. We have a little bit of the transport control, we have a little bit of the surface control. That means we have a curved calibration, but not as strongly curved calibration. So in a nutshell, we have these 3 calibration curves. And now, why am I showing it to you? Because often we hear the question, what is the right calibration function? And must I always use different functions for different components? Why isn't there a one-size-fits-all calibration? We have a surprisingly simple suggestion for you. Interested? Let's have a look. On this slide, you will recognize the chromatogram from earlier. From this chromatogram, I've selected calibrations of mannitol, xylol, and fructose to highlight the various calibration curves we discussed previously, and you see that we can observe them in practice. Please pay attention to the calibration equation. I'm not sure whether you can decipher them. The letters might be a little bit small, but let me tell you that we are using one and the same calibration form, not the equation itself, but the equation form model for that. And that is quadratic, without origin, so no forcing through the origin, and applying a weighing factor of 1 over amount squared or 1 over x squared. And we apply that for all the calibration curves, be it linear or curved or strongly curved. Now, where's that coming from? It comes from a straightforward exercise. We looked in literature, and we found that statisticians agree that there's almost a universal calibration function. And you can apply it to both linear and nonlinear calibrations, and the weighing factor ensures the higher calibration concentrations do not dominate the calibration. So, quadratic, no forced origin, weighing factor of 1 over amount squared, depending on, or 1 over x squared, depending on the chromatographic system. Now, in our example, we have calibrated over 3 concentration decades with 11 levels for 17 components, and all are using the same calibration model. All provided the best possible fit, ensuring the highest reproducibility. The chosen calibration approach significantly influences the performance and quality of your data. So quadratic, without origin, a weighting factor of 1 over amount squared. It's worth a try. And utilizing existing data saves you time and effort because you already have the data. So switch to the recommended calibration model and compare the reproducibility, recovery, amount deviation, the usual values that you use to justify, to validate a calibration. Don't rely on the correlation factor or its squared brother, and don't rely on the RSD of calibration. Instead, adapt the so-called relative standard error, RSE. These steps align with the latest developments in standardized methods, and surprisingly, statisticians seem to agree unanimously. So give it a try with existing data, evaluate the improvement, and then decide which path to take. Now, this brings me to the last part of the presentation, the conclusions. Now, what did we talk about? We did talk about the hardware. We did talk about the columns. It is the combination of a dedicated improved and specifically developed carbohydrate analyzer with the SweetSap column suite that gives you the performance that you saw. And that leads to all the applications that you can find on our homepage, www.antechscientific.com. And all these applications, from agave syrup to beer to instant coffee to lactose-free products, all these applications are guaranteed. Now, coming to the conclusion, we did talk about carbohydrate analysis using a dedicated system. We did talk about the hows, how to separate, how to deprotonate, how to detect. We talked about the detection itself, the detector cells. We did talk about the superior chemistry of the SweetSap columns. And there's one additional aspect that I would like to highlight. Did you know that the chemicals that we are using to do the separation tick mark basically a lot of bullet points of the green analytical methods? And we go even a step further. At Antech Scientific, we favor solutions that minimize the environmental footprint of our solutions, and that's why we favor our 2.1 millimeter applications, because that reduces all the eluent being used, and there are a lot of other benefits like increased mass sensitivity and decreased labor in the laboratory by using these columns. With that, I would like to thank you very much for your attention, and I think we are ready to answer your questions. That is the point where I give the word back to you, Daniel.
Yes. Thank you very much, everybody. Now we are going to the Q&A session. So first, I want to thank you for participating, and we will answer your questions as many as we can, but I see that there are already a lot of them. So if you don't get around to answer your questions on this webinar, we will try to answer it offline and let you know what the answers are. And please do not forget to provide your name and email address with them. Christian, Detlef, you both presented, and I will assign the questions to the one of you whose expertise best fits the question. So be careful, you don't know when it will be your turn. Okay, are you ready, Detlef, Christian?
No.
I'm afraid no.
So, first question, somebody asking, why do amino sugars elute in front of their corresponding neutral sugars? I think this is a question for Christian. So I repeat, why do amino sugars elute in front of their corresponding neutral sugars?
Okay. Yes. So the question is actually answered during my presentation, but I will repeat that. So it's a good question. We have to look at the difference in their molecular structure. The amino sugars, they have amino group in place of hydroxyl group for their corresponding neutral sugars. This means that in the same pH, the number of hydroxyl group in the amino sugars that can partially be deprotonated is less than their corresponding sugars. Or in a more simple term, the negative charge density of amino sugars is less than the neutral sugars. And this leads to less retention and therefore faster elution.
Thank you, Christian. The next one is also for you. It's can I use the SugarSap columns in other systems?
Oh, yeah, thank you for your question. It made me smile. I think what you meant is SweetSap instead of SugarSap. And yes, the columns can be used in other HPLC systems, but we really recommend using it with our ALEXYS Carbohydrate Analyzer to achieve the superior results that you deserve to have. SugarSap is a cool name, by the way. Maybe I will later talk to Martin about changing the name.
The next question is for Detlef. Will cooling the sample keep bacteria away?
You know what that reminds me? It reminds me to a sentence saying an apple per day keeps the doctor away. Now, well, will cooling help preventing the bacteria contamination? No, it will not prevent. It will slow down, and that's why we talked about cooling quite a lot in the past. You also heard Christian talking about heating the autosampler. So the question must be, what can we do to prevent bacteria contamination? And there are several chemical additions that you can do to the transfer solution or even to the standards, the samples themselves. So one of which is sodium azide, and the other one is acetonitrile. So you can add these bacterial poisons to the sample without affecting the analytical results of your analytical determination, and at the same time preventing any hiccup due to bacterial contamination.
So the next question is again for Christian. Interesting idea of using nitrogen. It would reduce the cost. What quality do you suggest?
In our laboratory, we use the nitrogen 5.0, so that's purity of 99.999%, so 5 nines. And in the field, there are a lot of cheaper, lower quality alternatives. So for example, nitrogen 4.6 or 4.0. But from my experience in the lab, this quality is not good enough for HPLC purposes. So nitrogen 5.0 is good enough.
Okay, thank you. So I have another question about the gases, and I think this will be the last one because we are very short of time. It's also for Christian. Why sonicate? Isn't the inline vacuum degasser enough?
Well, sonication is a step to degas. So the use of nitrogen sparging will introduce some gas dissolve into your mobile phase. And well, usually inline degassing can be enough depending on how good the quality of degasser. And in our case, we just sonicate because taking an extra step for precaution is always good, right? To ensure just reproducible results, ensure that there is no dissolved gas, and ensure good quality of your analytical data.
So thank you, Christian. So separations. What did you do to achieve this separation property?
Very good question. So what we did is we optimized all the steps required to prepare the stationary phase. We developed a core, a central particle that has a diameter of 5 micrometers. It's monodisperse. Monodisperse translates into low impact on diffusion, and low impact on diffusion means that the peaks get sharper. The sharper the peaks, the better the separation, the better the resolution. But that is only part of the story. You heard us talking about the nanoparticles, the pellicular design of the sweet sap columns. It is these nanocolumns on which we perform the separation itself. And the smaller the particle size in liquid chromatography, the more efficient the separation. And again, improvement in efficiency. Now, you heard me talking about quaternary amines, and with the AEX20, I talked about quaternary amines and ternary amines. So we pick and choose, we optimize the functional groups of the ion exchanger so that they meet our application needs that we define in advance to the separation. And last but not least, what I haven't touched base with is the organic rests that are being used for the quaternary amines. It is the selection of the properties of these organic rests on the quaternary and ternary amines that define the absorption and desorption, the interaction with the stationary phase, the interaction with the ion exchanger, and all this together. This is the secret behind the separations that you saw. That is the secret that leads to the sweet SEP column suite that we offer.
Thank you very much, Detlef, for this answer. So we are running short of time, so I tried to squeeze in 2 more questions, but please keep it short. So the next one is also for Detlef. Can I use other bases like KOH? If you agree, why do I experience a larger background with KOH in contrast to manually prepared sodium hydroxide of similar concentration?
Whoa. Well, let's dissect the question. There are a couple of keywords in that. That is KOH and NaOH, so potassium hydroxide and sodium hydroxide. Can I use either of those? The answer is yes. You can use either of those as an eluting component because it is not the cation that determines the interaction with an anion exchanger, but the hydroxide. The hydroxide is the same for both. But there's something else. You mentioned manually prepared sodium hydroxide, and you mentioned potassium hydroxide and an increased baseline noise. So if the one is manually prepared, I assume the other one is not manually prepared and could be electrolytically prepared in an eluent generator. Now, if you use an eluent generator, then you produce hydrogen. And if you produce hydrogen, you need to make sure that your eluent is properly degassed. So my advice for you would be to go back to the hardware and check that the high pressure inline degasser of your device, of your eluent generator, is working properly. Then the background noise should be lower as well. So just to summarize, sodium hydroxide, potassium hydroxide, you can use both.
Thanks a lot, David. So the last question is for Christian. It is interesting point regarding the post-column addition of sodium hydroxide. I think I will have to try it. Are there any guidelines?
Interesting questions, I would say. Guidelines about post-column addition. Well, it's given that you need an extra pump, of course, and the post-column pump should have sufficient back pressure and should deliver the sodium hydroxide without significant pulsation. Additionally, the concentration of sodium hydroxide should be about 200 to 300 millimolar, and the flow rate of the post-column pump should be about 1/3 of the flow rate of the main pump. I think those are the general guidelines for the post-column addition of sodium hydroxide.
Thanks a lot, Christian. You mentioned efficiency, particle size, and throughput. But what about selectivity? Can you highlight how you improve on that, say, with your AEX20 column?
That's an expert question. So, yeah, well, efficiency and efficiency and resolution can be addressed using particle size. The selectivity, however, is being addressed by the choice of the quaternary and ternary amines. You chose the AEX20, right? And the AEX20 uses a quaternary and a ternary amine, and that choice influences the separation capability of the column, and that's what we see in the selectivity. However, there is more. Selectivity is largely influenced by the organic rests of the quaternary and ternary amines. So we pick and choose these rests in a way that we can fine-tune the selectivity of the separation, of the interaction, absorption, desorption, and that's what we do. So it's a deep knowledge of polymer chemistry and a deep knowledge and understanding of the organic rests and their impact on the separation.
Thank you, Detlef. So the next question is also for you. Sorry, but why again was the sensitivity at higher hydroxide concentrations higher? Shouldn't it be lower?
No. You know, the sensitivity has to do with the availability of, the availability of oxoanions. And you know that carbohydrates are being deprotonated at high pH values. So we do not only need the high pH for the separation, we also need the high pH for the oxidization reaction in the gold electrode. And now I think it becomes clear, the higher the pH, the more the carbohydrate is deprotonated and the easier and the more the oxidization reaction at the gold surface can happen. And vice versa, the lower the pH, the lower the deprotonation rate, the lower the oxidization rate, the lower the sensitivity.
You? So, okay, I think that it's time for a change. So I am addressing the next question to Christian.
Oh, my turn.
It's your turn. Question is, how can I get rid of the bacteria in the autosampler?
I think this is related to the autosampler temperature of 40 degrees that I told you about earlier. Yes, you might have an increase of bacteria appetite, and that might cause some problem. But don't worry. I mean, bacteria are everywhere, so it's rather impossible to remove everything. But at least what you can do is to minimize and to eliminate the bacteria in your flow path. For example, by adding sodium azide to your transport liquid or even to your sample. Most likely at a low concentration, probably about 10 milligram per liter. That should be enough.
Thank you. So let's have a look at the time. So for sure, one question, maybe the last.
No,
it will
maybe
be
two.
addressed to Detlef. The question is, can I use acetonitrile as an element modifier?
Can I use? The answer is yes, you can. But the question is, should I use acetonitrile as an element modifier? No, you shouldn't. The reason for is you will not destroy the column, you will not destroy the element, the instrument, you will not destroy the cell. But what you are going to observe by using acetonitrile is a passivation of a reversible passivation of the gold electrode. And if I remember the literature correctly, then this is due to the interaction of the free electron pair of the nitrile function with the empty orbitals of the gold electrode, and that leads to the passivation of the gold electrode. I said you shouldn't. Well, if your desire for sensitivity is not so high, and you have high concentrations, you might get along with the acetonitrile addition to the element. But the question is, why would you add acetonitrile?